So now we're going to talk about the Laplace of the derivative and also the Laplace of the convolution. But let's start off with the Laplace of the derivative. I have the formula here. The Laplace of the nth derivative of f is equal to s to the nth power times the Laplace of f, that's capital F of s, minus s to the n minus 1 times, notice the difference, small f at 0, so this is the original function at 0, minus s to the n minus 2 times f, the derivative, again small f, the original function, at 0, minus dot dot dot, minus the n minus first derivative of small f at 0. So you see that in order to take the Laplace of a derivative of a function, we've got to have some initial conditions. So thus, IVP, initial value problems. That's what we'll be getting into. So I've got an example here, y double prime plus y equal to 1, where y of 0 equals 2 and y prime of 0 equals 3. So I'm going to take the Laplace of all this, and let's find out what the Laplace of y is. So we're going to take the Laplace of y double prime plus y, and what you do to one side, you must do to the other, Laplace of 1. So now I have that. Now we're going to use the fact that the Laplace of a sum is the sum of the Laplaces. So the Laplace y double prime plus the Laplace of y equals, and if you don't mind, we'll go ahead and do the Laplace of 1, which we know is 1 over s. Now, let's apply this formula for the Laplace of the derivative. So the Laplace of y double prime, well, n is 2 in this case. So what would I get? I would get s squared, because n is 2, times the Laplace of y, I'll do a capital Y of s, minus s times y of 0. So I'll just go ahead and put y of 0 minus y prime of 0. Notice there is no s on this last one. No s right there. Then plus the Laplace of y, which again is capital Y of s, equal to 1 over s. So now let's plug in. So I have, and let's put together our y of s's here. So I have s squared plus 1 times y of s. That took care of that term and of that term. Okay? Now let's plug in. So I have minus s, well y of 0 is 2. So that'd be minus 2s. Y prime of 0 is 3, so minus 3. So 1 over s. So I get s squared plus 1 times y of s equals, take this over the other side, 2s plus 3 plus 1 over s. So then all I got to do is divide everything by s squared plus 1. So what do I end up with? I'll end up with capital Y of s, because these cancel here, equals, well look what I got. I've got 2 times s over s squared plus 1. Then I've got this one, plus 3 over s squared plus 1, plus 1 over s times s squared plus 1. So that's what I get for the Laplace of this derivative, and I can solve for the Laplace of the original function now. Now, I do want to, before we head on to look at convolution, I do want to make note that if you look at these, and this is very important, especially these first two, I can find the inverse Laplace of them. This one I can do by partial fractions, but I also can do it by what I'm about to look at, convolution. So here's the convolution of f and g. Convolution of f and g is the integral from 0 to t, f of tau, g of t minus tau, d tau. And if you remember in class, we showed that it doesn't matter about the order of f and g. It doesn't matter which one you choose to be the tau function and which one you choose to be the t minus tau. Always I choose the easier of the two functions to be the t minus tau. What's the Laplace of the convolution? The Laplace of the convolution is the product of the Laplaces. This is the closest we get to a product formula. So I've got an example here. The Laplace of the integral from 0 to t of sine of tau, cosine of t minus tau, d tau. Now this integral would be very hard to do because I'd have to know some sort of trig identity to do cosine of t minus tau. So the one thing I notice is if this is my f and cosine is my g, look what I've got. I've got f of tau, g of t minus tau. So this is really the Laplace of sine of t convoluted with cosine of t. Now I know the Laplace of both of those functions. So the Laplace of sine of t, of course, is just 1 over s squared plus 1. The Laplace of cosine of t is s over s squared plus 1. So I get s over s squared plus 1 quantity squared. You see how easy it is to know this is the convolution and to know that the Laplace of the convolution is the product of the Laplaces. Now going in the opposite direction, I want to find the inverse Laplace of 1 over s times s squared plus 1. Now, rightfully so, I could use partial fractions. But the one thing I notice is this is a product. It is the inverse Laplace of 1 over s times 1 over s squared plus 1. Well, why is that important? Because that's the end result of the Laplace of a convolution, is the product of the Laplaces. So what is 1 over s? Well, 1 over s is 1. The inverse Laplace of it is. What's the inverse Laplace of 1 over s squared plus 1? That would be sine of t. So I have that the inverse Laplace of 1 over s times s squared plus 1 is 1 convoluted with sine of t. Now I'm going to bring that up here. So this is going all the way over here. Now, pick the easier of the two, because I don't want to have to use some trig identity to look up. Well, the easier of the two is 1. So this would be the integral from 0 to t. I'm going to put the t minus tau in the 1, so I don't have to deal with it. So that'd be 1 times, so I'm going to put the tau, f of tau is going to be my sine. So that'd be sine of tau, d tau. So we know what the integral of that is. Well, that's going to be minus cosine of tau, evaluated from 0 to t. So what do you get when you plug in? You get a minus cosine of t, you get a plus cosine of 0, which is 1. So you get 1 minus cosine of t. You see how easy it makes it when we know it's the convolution of two functions. Again, I can pick which one of the two is going to be my tau, which one of the two is going to be my t minus tau.